Okay, guys, we are now going to calculate area. So again, welcome back to basics of math, this time geometry. And we're going to exclusively do areas of rectangles. The tricky thing is we are going to use those rectangles and the summation notation we just learned to calculate areas of things that are not rectangles even the slightest bit. And first we're going to do some approximations. That's what the summation notation is good for, is approximations. And then we're going to get exact, and then cool stuff will happen. So first of all, let's go back to our last function. We had f of x equals, what was it, 4 minus x squared. Okay, let's look at this from 0 to 2. So right away we have something that should look familiar. We have an lower bound and an upper bound, and we are going to split that into a certain number of things. Now, unlike last time, we're going to actually make it a little bit more regular. I will possibly put up a video showing you what this would look like using the exact numbers we came up with last time, to show you that you don't have to make it regular, but making it regular is faster and you can do more with it. So let's look at a regular example, because we can actually use some of our algebra techniques instead of just doing craziness. So let's divide this up into, let's say, okay, that's fine. Let's be boring and do, let's just be boring and do 4 sections. I guess I'll do a little bit more interesting one where we do a different number of sections, so it's a little bit less boring. So what do I mean by that? Well, we've got from 0 to 2. Remember, this is at 4 and it goes like this. It's an upside down parabola. What we are actually going to do is we are going to break this section into from 0 to 2. We're going to break it up into 4 equal sections. And what we're going to do is we're going to build rectangles to estimate the area under this curve, between this curve and the x-axis, in other words. So if this is divided up into 4 equal sections, what are the section boundaries? Well, half of 2 would be 1, and then this would be 1/2, and then this would be 3/2, or 1.5, or however you are used to doing that. Please don't use mixed numbers. Mixed numbers are evil. All right, so what does this have to do with rectangles? Well, remember, rectangles, the area of a rectangle is just base times height, or length times width. In this case, we are going to calculate, we already know the base, because we are going to build these rectangles up like so. And like so. Okay. So we already know the base for each rectangle. The base of the rectangle is, well, let's just do one thing at a time. So before we make this up into a sum, we first have to realize our first section is from 0 to 1/2. So in other words, this is this is x1, this is x2, this is x3, this is x4, and this is x5. Why x5? Well, we have 4 sections, but remember there's the first one. You always have to remember the first one. Some people start this at 0, so you end with the number of sections that you're going for. Let's just keep it the way we did it in the last video. But yes, this is from x1 to x2. Our next rectangle is going to be from 1/2 to 1. The next one is going to be from 1 to 3/2. And then the final one is going to be from 3/2 to 2. Now, we know what each of these widths are, right? The base here is x2 minus x1. Oh, look at that. In other words, this is delta. We're going to use x1 in this case. Delta x1. So from x1 to x2, that's a distance of 1/2. Okay, and then the difference here, our delta x2, is also 1/2. They're all, in fact, 1/2. But remember, with the last example, they can be all different. We could do it all different, but then each difference would be its own thing. In this case, they're all the same, which is nice. Okay. So we at least have the base of our triangles. So let's give ourselves some space here. All right, the base of our triangles. Okay, base of our triangles is just 1/2 each time. So let's actually do a 1 is 1/2. That's the base. What is the height? Well, for the height, we're going to take the actual y value at that point. We're going to multiply by the y value at x1. Okay, the area for the second one, I'm going to rearrange the order a little bit. We're going to do the y value at x2 times delta x2. But again, that's just 1/2. For the third one, we have the y value at x3 times delta x3. Again, this is just the base times the height at x3. That's the area of this rectangle, which gives us a little bit of an idea of the area of the function between those two values. And then for the fourth one, we have f of x4 times delta x4. Okay, so this may look familiar. What we can actually do is find the find the sum from I equals 1 to 4 of each of the 4 areas. And that will add the areas of the 4 rectangles together for us. And then we have an estimate for the area. So that would be, because we now have something relating the area to the index, we can actually do equals 1 to 4 f of x sub I times delta x sub I. But as we just did, all of these are 1/2. The constant 1/2, so that constant can come out front. In other words, we have 1/2 times the sum from I equals 1 to 4 of f of x sub I. Now, again, these are just the y values. So starting with the y value at x1, which is 0, let's actually give ourselves some space and actually calculate this. Let's actually do it right here. Okay, all of these are a half. Okay, f of 0, we already calculated that. 4 minus 0 is 4. 4 minus a half squared is 4 minus a fourth. In other words, 15 over 4. 4 minus 1 squared is 3. And then 4 minus 3 halves being squared. In other words, 9 fourths. So we have 16 fourths minus 9 fourths. In other words, 7 fourths. Okay, so what we're actually doing here is we have 1/2 times adding 4, 15 fourths, 3, and 7 fourths all up. Okay. 4, I'm not going to do these in exactly the right order. 4 plus 3 plus 15 plus 7 is 22 fourths. In other words, we have a 7 here, so 28 fourths plus 22 fourths is 50 fourths divided by 2 is 25 fourths. All right. Now this is an approximation of this area. It's not exact. As you can see, the actual function does not include a little bit of this rectangle here, a little bit of this rectangle here, a little bit of this one, and a little bit of this one. So in other words, this is bigger than the actual area under the curve. I'll do another example later of a way to get another estimate that's lower, and then we have sort of the area is between these two things. But for now, I'm going to stop here.